Here is the content of the sheet metal class. We will touch upon three subjects: how to develop spiral shaped sheet metal parts, how to calculate or reverse engineer the developed length of the sheet metal bends when the bends are larger than 90 degrees, how to assign sheet metal bend lines to layers is the third topic. On the sheet metal side, there was an interesting discussion that happened a couple of weeks ago internally with one of our application engineers, and we learned a lot of this. That's why I wanted to present it here. The question was, how can we create flat patterns for sheet metal parts that are based on a 2D spiral? Typical examples I can think of is watch industry, or the industries making batteries. They very often have very tight spaces where they want to put a lot of surface area. The procedure is a little bit long-winded to get to a good result, but and on top of that you have two possible ways of getting there. There is the first method that I would call like the contour flange method. Second method would be using a thicken command. Both will give you the same result. It depends on what you prefer. The initial problem we have is that Inventor does not have a spiral function in a 2D sketch. You can only access the spiral function in a 3D sketch, and that's not necessarily what we want here. Clearly, what you can see from the image here, that the spiral that we are looking at is a two-dimensional spiral. So how do we solve this? The first step is to get the spiral function where we have it. So we start with a 3D sketch in a sheet metal part, or you convert a regular part to a sheet metal part and then invoke the 3D sketch function. We concentrate on the spiral drop-down in the helical curve command. It's the last choice in the drop-down. Then we define a work plane normal to the axis of the spiral, and we create a 2D sketch on that work plane. And then a very crucial step in the whole process is to use the project geometry command to project the 3-dimensional spiral on the 2-dimensional sketch. At that point, 3D sketch can be made invisible. The second crucial step to make it work is on the projection to use the break link command from the menu. Like I indicate here, put it in yellow so that everyone is clear about it. This step does something special that makes it work. And then finally, continuing with the procedure, you can bifurcate here and go for two different options. The contour flange just uses the 2D sketch and it does everything for you. Or you can decide to extrude the sketch as a surface and then thicken the surface with a thickness equal to the sheet metal thickness, of course. Otherwise you would not be able to develop the shape. And the flat pattern command will work. Here is an example of the battery industry where we not only did the spiral shape, but on top of that we managed to squeeze in 800 different cuts in the sheet metal part. Here is a demonstration on how to create a spiral with a contour flange function in order to develop it in a sheet metal part. Like I said, sheet metal, so I need to start with the sheet metal template, of course. By default I get a 2D sketch. I'm not really interested in a 2D sketch right now, so I delete it for now. What I want is a 3D sketch, and in that 3D sketch I'm interested in the helical curve. I have no construction geometry, so I first need to create some geometry that would designate the normal to my spiral. So I start from the origin and I create a 100 millimeter long vector here. Okay, and I use this to base my spiral on. The key here is to go to the spiral drop down. By default you will have one of those other options which generate a 3D spiral. I'm interested in a two-dimensional spiral in a 3D sketch at this point. So I'll fix the starting point here. I use this second point as my normal. And now I can have a look on what I'm doing here actually. Let's go to the right view. I have a pitch of 10 and I'll take like 5 revolutions. Diameter, let's do something like 50 or 100 maybe. Okay. This is sufficient in my three-dimensional sketch. At this point I go back to a 2D sketch, which I can base on that same plane of the spiral. For didactical reasons I place that sketch on an offset distance. So I create my sketch here. I use the projection to turn my 3D spiral in a 2D sketch. At this point the 3D sketch is no longer needed. And in my 2D sketch I need to do an extra post-processing operation to make it work, and that is really key here. I need to break the link with that 3D sketch, otherwise the development of that spiral won't work. So I use break link, it adds extra nodes, and from here on it's cruising really. With this line I can use the contour flange function. I forgot to check in my sheet metal styles what I have here. Let's say I want a 2mm thick sheet metal plate, and I use contour flange, select my flange, and at this point I can develop my flange. Here is a demonstration on how to create developed parts starting from a 2D spiral with using the thicken function in Inventor. So because I want to go to a developed length, I start with a sheet metal template. The spiral function that I'm going to use is situated in the 3D sketch panel, so I remove my initial 2D sketch and I go to a 3D sketch. Because I have nothing in here, I need to create something to attach my geometry to, so I'm just creating here a line that will serve as my perpendicular line to the plane of my spiral. So I start from the origin point and I go 100mm in one direction. So nothing fancy here, it's just the normal to my plane that I will be constructing on. The function that I'm interested in is the helical curve function. I don't need the 3D precise toolbar anymore. And in that function I'm navigating to the spiral option, which allows me to create a two-dimensional spiral. The system asks me to create the start point of the spiral and the normal, and then I can input the diameter and the number of revolutions, so I'll take 5 here. Pitch 10 is fine. So this is how the spiral looks like. I now want to turn this into a solid, of course. First of all,
key point here is that you cannot work on the spiral itself. So you have to make a projection. So I create an offset work plane at the end of this vector here, and I'll create a two-dimensional, a 2D sketch is sufficient. Go in here, and I project my spiral. That sketch can be superposed to the original plane of my spiral. It doesn't really matter, but for didactical purposes, I use an offset plane. At this point, you don't really need that 3D sketch anymore, so you can make it invisible. And here you are. I could be tempted to start doing my 3D construction here, so I extrude my spiral, make it into a surface. Let me rotate a little bit, and then I'll check with my sheet metal style to see what my thickness is. I'm not too happy with 0.5. Let's say I want to do something with 2 millimeter thickness, and the first method is to use thicken. If I would find it, oh, it's over here. So I use thicken, and of course I use the same thickness as in my sheet metal style, which is 2 millimeter. Then I could think that everything's fine and just go for the flat pattern, and you see what happens. It doesn't work. So the step that I forgot here was in the 2D sketch phase. In order to develop this particular spiral, I need to add an extra step, and that step is to break the link with the original 3D spiral. This break link function, you will see, it changes the geometry slightly by adding several nodes to the sketch, and this behind the scenes operation makes it work. That's the best I can describe it. It's all kind of magic, but we're working on it with our ASM team to include this workflow in the next release, 2012 release I mean, and we hope that the workflow will be smoother there. So once I've done this break link operation, you will see my flat pattern work successfully.
For sheet metal, we want to talk a couple of minutes about calculating the developed length. Many customers are curious and want to reverse engineer on how we calculate the developed length, and here is a case that came to me where a customer had a very simple example with a bend larger than 90 degrees, and he could not figure it out what the correct developed length was. The unfolding rules as we present them in the sheet metal styles are similar to this picture. So this is the bitmap you will see when you open the sheet metal style editor. And the unfortunate thing of this image is that we show our bend angle beta for a situation smaller than 90 degrees. So we indicate where beta sits. We show you the developed length formula even here on top. So a good start, but it doesn't tell the whole story. The values of L1 and L2 that you see here and here are calculated differently for a beta larger than 90 degrees. I just want to make a side excursion to what happened between 2009 and 2010. Prior to 2010, we based the developed length calculation on the bending angle. Since 2010, we based on the open angle. Just for illustration purposes, this is the K-factor formula where you see the beta value included. This is the formula we use since 2010. The benefit of making this small change is that the open angle calculation is much more robust and will still work for extreme angles like 180 degrees. On the next slide here I'll show you how this looks like for a very particular example of a sheet metal plate of 0.06 inch thick and with an inside radius of 0.125 inch. This is the way the bend allowance evolved versus on the horizontal line the bending angle. That was how this graph came out in 2009. When you do the same graph in 2010, you see that for all bending angles from 0 to 180 degrees, you have a smooth increasing linear curve. So enough mathematics. I think the key point is how can you reverse engineer the length on a sample part. And here is a picture of that sample part. It's very simple. There's just two flanges actually, and we introduce a custom bend equation that you see here. I'll show it much better in the demo that follows. The bend deduction formula is just the bend deduction is proportional to the bending angle, and we simply divide by 90 degrees. Inventor gives us a developed length which is equal to 55.738 millimeter for a bending angle of 120. How can we correlate this to what we manually can calculate? The next video shows how we would do that.
In this demo I will explain the reverse engineering of the development rules that we use in Inventor when using a deduction customized by a user. So I start with a sheet metal template, and I start from a very simple shape which is rectangular. I want it to be 20 by 40 as my starting face. And I turn it into a face. Let's check the style to see if the thickness is what I expect. So I want it to be 1 millimeter, and we'll have a look at the unfold rules. Like I said earlier, we want to customize the unfold rules. Rather than using the linear or bend table, I'm going for custom equation, and I want the customization to happen on a bend deduction. As you see here, the formula is that the developed length is L1 plus L2 minus D. The image shows here those values of L1 and L2, and also the value of the bend angle beta. Keep in mind that this image here shows the situation where the value of angle beta is smaller than 90 degrees, and this is the misleading part of the whole story. So we will be examining a situation where beta is larger than 90 degrees. In order to customize, we need to fill something in our custom formula. I will be using a very simple modification where I make the deduction delta related to the angle beta simply divided by 90 degrees. To satisfy the units in my formula, I need to add a length dimension or a length unit. In this case, I want it to be calculated in millimeters, so I add 1 millimeter as a multiplier. So you see now my formula is no longer red, and Inventor is happy with it. Here's my formula. I save my edits, and I now use this formula here. So in order to test it, I need to add a flange, of course. let's first try with a flange which is 20 millimeter high. So as you've seen from my sketch here, if I display my sketch, so I have a 40 millimeter first flange and I have a 20 millimeter second flange. So this is 40 plus 60. So what does that give in the developed length? If we check in the extents, so we have 40 plus 20 minus 1, which comes from the 90-degree angle divided by 90. 90 divided by 90 is 1. So we can perfectly explain what happened here. The more complicated situation is where my angle of my flange is different from 90, and I make it, for instance, 120. So it flips over to this side. If you would use the same formula of 40 plus 20 minus 120 divided by 90, you come up with a different value from the value that inventor gives you, which is 55.738. We will explain in the next presentation and in the slides how this value is calculated.
Here is how we calculate the developed length. The unfolding formula is pretty simple, so it's just L is the sum of L1 and L2 minus the deduction. In this case, deduction is beta divided by 90. Beta is 120, so 120 divided by 90, and we come up with a value of 1.333 millimeter. No discussion about that. What are the values of L1 and L2? That's really the key here. If we temporarily bend the 120 degree angle back to a 90 degree angle, you see that L1 is 40 and L1 is 20, excuse me, and L2 is 40. So you would be tempted in a first rough calculation to say, okay, my length is 40 plus 20 minus 1.333, and you come up with a value of 58 something. This is absolutely wrong. This is not the right way of calculating those values L1 and L2. The correct way of calculating them is as follows. You have to take the tangent point, and the best I can explain it here is look at this drawing view where I zoomed in on this the bend detail. You see clearly where I take my distance from. It's the tangent line in the vertical direction and the tangent line aligned with the direction of the second flange. That gives us the value of L1 and L2. And if we bring those values in, you come to a value of 55 dot something, and this is exactly the value as is presented in the sample file. You can download the sample file from the resources section. Another interesting case with sheet metal parts is around the bend lines and how to export those bend lines to AutoCAD, for instance. Once you end up in AutoCAD, users are much more aware of what layers those bend lines go to. So here is an example of a very specific demand where we have, just to focus attention quickly, we have a very simple sheet metal part with a couple of bends. You see 4 bends are up in this bend table and 2 bends are down. The particular question that we want to solve here is the following. The user would like to store his bend lines on 2 different layers depending on the nature of the bend. He wants the bends that go up go to a layer called up. The down bends, he wants them to go to the down layer. At the same time, he wants to give a different line style to the up orange, for instance, and a dashed line for the down bending line. and it does the same for a different style for the so they can easily be spotted even on a black and white plot or when exported to AutoCAD as DXF. So how do we go about doing this? I used a macro to solve this puzzle, and it clearly, prior to exporting to Dwig or DXF, the process is of simply selecting your drawing view, and hopefully there's a sheet metal part in it, and the bent lines will automatically be assigned to a bends up and a bends down layer. If the layers do not exist in the drawing styles, this is very well possible for existing or older drawings, the macro will create those layers automatically for the user. This way the macro works on existing drawings. Of course, if you can prepare your drawing templates with those two layers already in there, you have to respect the syntax, so it has to be bends up, bends down in capitals. There is a dataset attached to this training which you can download from the resources area. What is the result of the macro? So I'll show you the situation before running the macro and the situation after running the macro. So the macro here shows that I color coded the up lines, the up bent lines in orange with in a dash dot line, and the bend down lines in a blue color. When you export to AutoCAD, there should not be any change. The layers are all preserved, color is preserved, so you should be fine to make the distinction in a visual manner before you even send the flat pattern to a bending machine. Let's have a look at how to give special layers to bend lines in sheet metal. Here's an example of a drawing where I prepared a bend table and the drawing view. I'll show you the drawing, the part as well. It's not very spectacular, but it just has enough bends to show you the different types, the bend up and the bend down lines. So you see there are 1, 2, 3, 4 bend ups, if I may call it like that, and there are 1, 2 bend downs in this part. So how do we convey this in the drawing? You can look at the table, of course, and figure it out from there, but the purpose of the macro that I will present is to make life easier for the user. I'll show you how the macro looks like I'll give a bird's eye view. It's not that you need to know the full details of it, but basically what I'm doing is I'm doing a backup of all the selection sets, and then I make sure if the layers called bends up and bends down exist. If not, I'll create them in the next section here, and then I just go through all the edges, and if it's an up edge, I assign it to a particular layer. If it's a down edge, I assign it to the other layer, and that's basically what it does. So this is as far the code goes. How to put it in action is pretty simple. You just go to the macros section and use the assign bend lines to layer thing and run it. If I don't select anything, you get this warning dialog. So it tells me that I need to have something selected. So let me window select my edges here, then I will run that macro. So you see at this point there are different colors, different line styles created. If I go to the annotation tab and I select one, you see that the blue lines are on the bends down layer, the red lines
on the bend sub layer. If I go to the style editor, I've picked the chain line type for these lines, but you're free to pick anything else if you want to customize. It's perfectly possible. Let's wait a second before the style dialog comes up. So these are the layers automatically created. You can create them up front in the template file of the drawing, and you, of course, you can still customize. So if I want to have a dashed line or a dotted line, I take a dash, you can still do so. Okay. At this point you can export the drawing to an AutoCAD DXF or DWG. So let's do a DWG here. And when I open this in, let's use the viewer to open this file. So I just use the design review software just to go quick. You will see that the AutoCAD part, or the AutoCAD people will have a clear understanding of what the bend lines mean without even having to include the bend table. Okay. So I'll drag in my file. I will have a look. See here, the colors come over okay. I can play with the layers. It's all fully functioning.